Welcome back to part 2 of our discussion on the optional packages in MODFLOW. Today we are going to discuss the optional packages which are shown in bold here. These are ones that are used a little more frequently than some of the others. I just want to, before we get into the ones that are bolded, I want to highlight a couple of others here. First of all, this MNW and MNW2, multi-node well and multi-node well 2. These are advanced versions of the well package. The well package, as you may recall, we select a cell, we assign the well to a cell, and we give it a pumping rate. That's it. What if you have a well screen that spans multiple layers in your model? Or what if the well screen, with the water table drops and it can't pump the full rate? Well, several years after the well package was released, it was part of the original MODFLOW model in '83, but at some point they developed the MNW and then the MNW2 package, which provide a much more sophisticated representation of wells. You can have a well screen span multiple layers, and it automatically distributes the how much water comes from each layer based on the transmissivity of the layer and the heads in the layer. Something that's you just can't do with the well package. If the water table drops too low, it may cut back. Instead of the well going dry, it cuts back the pumping rate. In addition to specifying a pumping rate, you can have a pressure defined well. So instead of telling it how much water comes out, you tell it what the pressure is, the suction on the well, and then it determines how much water comes out. In a lot of cases, you don't need that sophisticated of a treatment, but it is available if you need it. The SUB or subsidence package allows you to simulate aquifer subsidence, where if you dewater an aquifer, certain kinds of aquifers, you can end up causing the effective stresses in the aquifer matrix to get too high, and it will cause the aquifer to compress and lose porosity. And you can simulate that with the subsidence package. There's the UZF unsaturated, I believe that should be unsaturated, not unsaturation, unsaturated zone flow package. That's for simulating flow in the vadose zone, which you don't normally need to worry about, but you can. The drain return flow allows you to take water that goes out to a drain and re-inject it somewhere else in the model. Let's see, the other ones, the lake package, that allows you to simulate in a very sophisticated way the interaction between a lake and an aquifer. The general head package that we'll talk about in this lecture does the same thing, but not at the same level of sophistication. So that's kind of a quick overview of some of the others. Now let's jump in and look at some of these, the packages that are highlighted with the bold lettering. So several of these packages relate to stream aquifer systems, where there's a connection between the groundwater and flow of water in a river or stream. When we're talking about rivers, we often talk about a gaining river if the water table is high relative to the stage or elevation of water in the river. The aquifer will lose water to the river. We call that a gaining river. A gaining river is also a sink. From the perspective of the aquifer, it's a sink because water is leaving the aquifer. If the stage in the river is higher than the water table, the the water levels in the aquifer, then you could have what we call a losing river, where water flows from the river to the aquifer. From the aquifer's perspective, we call this a source, and you'd have a positive flow rate into the aquifer. And then sometimes we have what are called disconnected rivers. That is, if the water table is sufficiently below the river and the sediments below the river are a lower permeability than the aquifer, which is often the case, then we can get a disconnected river where there's a partially saturated zone between the river sediments, the river bottom sediments, and the aquifer, and there's kind of a slow, gradual percolation from the river down to the aquifer. So the aquifer will effectively gain some water from the river. So it would be a source, and this would be a type of losing river because it's losing water to the aquifer. And we can simulate all three of these conditions with a number of packages in MODFLOW. The most commonly used package, and one which we will use this semester, is the river package. And as shown in this screenshot, if you overlay a river onto your grid cells, you mark those cells as river cells, you enter a stage and a conductance and elevation. We'll talk about those. And if the head in the aquifer is above the river stage, water flows from the aquifer to the river. If the head in the cell is below the river stage, water flows from the river to the aquifer. So that's, in general, you can simulate gaining rivers or losing rivers. So let's look at that in a little more detail. This is an idealized representation of a gaining river that we saw in the first slide, or the first slide on this particular topic. And then this would be an idealized representation of that system from the perspective of a cell, an individual cell in MODFLOW. Now, the cell doesn't look exactly like this, but for a given cell, we don't have all the geometry shown on the left. We just have a few basic parameters. So Hij is the head in the cell. In other words, the water table elevation in the cell. And then HRIV is the river stage. It's the elevation of the water in the river, which we call the stage. And then CRIV, that's the conductance of the river bottom sediments. And you calculate that the same way we talked about in our last lecture. And presumably these sediments have a different hydraulic conductivity than the surrounding aquifer material. It's not uncommon in your river bottom you get some fine-grained materials which are have a lower hydraulic conductivity than the aquifer. And so there's some head loss as you flow from the river to the aquifer, or vice versa, as the water passes through the river bottom sediments. RBOT is the elevation of the bottom of the river bottom sediments, and that will be important in a minute. We'll talk about that. And then QRIV is the resulting flow rate between the aquifer and the river. And that can be positive or negative depending on where we are. So for every river cell that when you're using the river package, you select a set of cells, you identify the cells where the river is located, and for every cell you have to input HRIV, the river stage, CRIV, the conductance, and RBOT, the elevation of the river bottom sediments. Those three values are user defined. The head in the cell is calculated by the model, and then Q, the flow between the aquifer and the river, is also calculated as MODFLOW runs. So now that flow rate And the interaction between the river and the aquifer is going to vary depending on the relative elevation of the head, HIJK, with respect to HRIV and RBOT. So let's talk about that. So we have three cases. Case number one, the head is above the river stage, as shown in this diagram. So this would be a gaining river. In this case, QRIV is defined as the conductance times HRIV minus IJK, the head difference. So in this case, the equation is identical to what we saw with the drain package. We just have a conductance representing the hydraulic conductivity and geometry of the river bottom sediments. And then we multiply that by a head difference defined by the difference in head between the water levels in the cell, HIJK, and the stage in the river. And the larger that difference, the greater the flow rate is from the river, from the aquifer to the river. And you'll notice that it's HRIV minus HIJK. Once again, that results in a negative head difference, which results in a negative Q, which is the proper sign because the flow rate is always defined from the perspective of the aquifer. And so a gaining river would require a negative Q coming out of the aquifer. Okay? Now, case number two, we have a losing river, and that means the head is below the river stage but above the river bottom elevation. So if you can see my cursor here, the head is below this HRIV value and RBOT. And so now, because of the head difference, since the stage is higher than the water table elevation, water flows out of the river into the aquifer, and we end up using exactly the same equation that we did in the previous slide. It's just the conductance times the head difference, the only difference being now that head difference is positive. HRIV minus HIJK is positive, so now we have a positive flow from the river into the aquifer. And then the third case is a disconnected river. And in this case, HIJK, the head in the cell, is below the river bottom elevation. And once that happens, the river and the aquifer become disconnected. And so it's no longer completely saturated between the river bottom and the aquifer because of the relatively lower permeability of the river bottom sediments. It slows the flow down, and then it just percolates down. Once it gets through the river bottom sediments, the water just percolates through the vadose zone down to the river. And you'll notice on the left here there's a mounding in the water table because of this water percolating into the aquifer. And so in this case, the flow rate is defined with this equation, where the head difference is now defined by the stage in the river minus the river bottom elevation. So this difference right here from the top of the river down to the river bottom sediments, that is the driving head that pushes the water through these sediments. And once it gets to that point, since it's now in the aquifer that has a higher permeability, it just percolates down. Now, how long does it take to percolate down? Well, it could take a few days or months theoretically, but we don't account for that in MODFLOW. We assume it occurs instantaneously. If you want to take into account the time required for that, you could use the unsaturated zone package, unsaturated zone flow. But in most cases, this is a relatively small amount of water, and the distances aren't great, and so we don't account for the time it takes for that to happen. Okay, so that's how this works for those three cases. The next question is, how do we come up with this conductance? First of all, you overlay your river network on your MODFLOW grid, and for every cell that is even partially overlapped by that river, you mark that as a river cell. And that becomes an individual entry into the river package input file. And then the next thing you do is for each of those cells where there's an overlap, you calculate the length of the overlap, and then you estimate, and that becomes the length of the reach as shown here. Then you estimate the width of the river, the thickness of the river bottom sediments, and the hydraulic conductivity of the riverbed material. And the water, whether it's flowing down or up, goes in the direction shown by the blue arrow. So to get the conductance, we do hydraulic conductivity times the area of flow divided by the length of flow. Well, the length of flow is this thickness of the river bottom sediments. The area of flow is the length of the reach multiplied by the width of the river. So L times W. So our conductance is calculated as K LW over M. In most cases, we just assume a constant width and a constant thickness M and a constant hydraulic conductivity, and that, so the KWM term is kind of the same through the whole river, and then you just take these individual lengths for each cell and multiply it by that term, and you get an individual conductance for each cell. So that's how we calculate the conductance for river cells. Now, that's the most basic way to represent a river. A few years after the river package came out, again, that was part of the original version of MODFLOW, they came out with some more advanced methods, one of which is the STR package, the Stream Aquifer Interaction package. In a lot of ways, it works identically to the river package. You still have a conductance, you still have the river bottom elevation, and water can flow from the aquifer to the stream or vice versa. And you can have the river can be disconnected from the aquifer if it gets deep enough, or it can be a gaining or losing stream. But unlike the river package, you do not input the stage. So you would use this in cases where the flow of water from the aquifer to the river has a significant impact on the stage, and you want to do some predictive simulations, for example, to see what kind of impact different fluctuations in the water level will have on the river. And so in this case, instead of specifying the stage, the flow is routed using simple channel hydraulics, and MODFLOW calculates a stage using Manning's equation. Now, if you've had a course on fluid mechanics or hydraulics, hydrology, you may have seen Manning's equation. Manning's equation is a technique, is a simple equation for calculating flow in an open channel, such as a river or a ditch or a pipe, a pipe that's not completely full. And U and N, U is a units term, N is a roughness coefficient, A is the cross-sectional area of flow, R sub H is called a hydraulic radius. It has to do with the geometry of the cross-section of the river, and S is the slope of the river. So these things can be, now I don't want to go into too much detail here, but this, most of this is geometry, and so you can also, that in this R sub H term is factored into that, and into the A term is the stage in the river. So for a given Q, it back calculates the stage And so if we look at the next slide here, this is a diagram from the STR documentation. So basically you define, again, you have these, you overlay your river with the grid cells, and you mark what cells are overlapped. But in this case, you put them together into a sequential series of what are called river segments. So for example, segment number 1, it would include 1, 2 reaches. Segment number 2, which is a canal diversion between 2 rivers, which you can do, has 1, 2, 3, 4 reaches. And they're ordered from upstream to downstream. Segment number 3 has 1, 2, 3, 4, 5 reaches, and so forth. And so based on this ordering, the model knows as water flows out of segment 1, it goes into segment 2, into segment 3, and so forth. And so at the for each of these segments, you input, if it's on the boundary of the model, you'd input how much water is coming in to the top. But then as this river crosses this cell, maybe it loses a little bit of water. And then, so by the time you get to the next cell, there's an incoming flow rate that is smaller than what it was up here. And so it recalculates the stage based on the water that it's lost. Conversely, as you go from one reach to the next, it could be that you gain water because it's a gaining reach. And so you take the water that, for example, suppose I'm looking at segment 3, reach 3. You take the water that came in from this reach and then add or subtract. Let's, for the sake of argument, say we're going to add water because this is a gaining reach. And that gives you a new Q down here. So for every cell, you have a Q that you can use to back calculate a stage. And then that stage then controls how much water is gained or lost. So your input for this, for each segment, that is a collection of reaches. You have to put the incoming flow at the top, the average width of the river, the slope, and then a Manning's roughness coefficient. And then for each individual reach, you input the conductance, the elevation of the bottom of the stream bed for when it becomes disconnected, and then the elevation at the top of the stream bed, which is required to do the calculations for Manning's equation. So that's kind of a really quick overview of this package. If you're not familiar with Manning's equation, that might be a little bit difficult to follow, but suffice it to say that it's in addition to, how does this differ with the river package? So in addition to determining gains or losses along individual reaches, it actually simulates the flow through the river and routes it from upstream to downstream. And so it's you're simulating not just the interaction of the river with the aquifer, but actually the flow in the river itself. And then there's another one called the SFR package. I'm not going to go into detail, but it's an even more sophisticated stream package. It has even more options for inputs to the stream. I believe you can have surficial runoff into the streams. And it does interact with the unsaturated zone flow package we talked about. So when you have a disconnected river, it will actually calculate the delay in water percolating from the river bottom down to the aquifer. So that's an even more advanced package. Okay, let's move on to the general head boundary package, the GHP. We call it the general head package, but the B stands for boundary. This is what we typically use to simulate lakes and reservoirs and how they impact an aquifer. It's actually a very simple package. The only two parameters you need are the head and the conductance. And when I say head in this case, I mean the stage in the lake, the elevation of water in the lake. And by the way, as you can see in this diagram here, you overlay the the boundary. Let's say this is a polygon representing my lake. You overlay it on your MODFLOW grid, and for every cell that is completely or partially overlapped by that lake, you mark that as a general head boundary cell, and then for each cell you give it a conductance and then a stage. And that stage for the lake could be either steady state or transient. And we'll talk about how to calculate the conductance. And so schematically, this is how this is sometimes represented in the MODFLOW documentation. The source would be the lake or reservoir. HIJK would be the head in the cell. Now, it doesn't flow through a pipe like this. This is just an idealized representation. And again, the idea is that there are sediments at the bottom of the lake, and those sediments cause a head loss as water flows between the lake and the aquifer, or vice versa. And the equation we use to represent this is the one we've seen before. Q is equal to conductance times the head in the source minus the head in the cell. This is looking at an individual cell. And the greater the head difference, the greater the flow rate. And if the head in the if the water table, the head in the cell is greater than the stage in the lake, there's water going from the aquifer to the lake, and that sometimes happens. And some mountain lakes, for example, are fed to a certain degree by groundwater. And so this can go in either direction, and using this equation we'll get the proper sign. So here's another way to if you want to look at it with a more realistic drawing. So this would be a cross section through your lake, and if the water table in the vicinity of the lake is higher than the stage or head in the lake, then water flows through the lake bottom sediments into the lake. Or if the water levels in the aquifer are lower than the stage in the lake, then water drains from the lake through the lake bottom sediments into the aquifer. There's no disconnection here. It's always connected. The assumption is that it's a really big and strong source, and so that everything remains saturated. Now, if you want to represent a lake, and if you believe for whatever reason that there's a disconnection below the lake, you could still use the river package to represent a lake. And by the way, I've seen cases where people use the general head boundary package to represent a river. So you don't get the disconnected case with a river. So how do you go about calculating the conductance? So this is, look, our lake bottom sediments cover an area, and suppose we have a cell in the location shown here. The water flows vertically through those lake bottom sediments, each of which has a thickness L, and the cell has an area A. That area, of course, is just based on the length and width of the cell, which is part of the grid geometry. And so the conductance then is just Ka over L. Now, if you have a cell that overlaps on the edge where it's only partially overlapped by these sediments, then the calculations are a little bit different. You take the fractional area of that cell that is covered by the lake, and that becomes the area. Now, fortunately, these calculations can all be done automatically for you using the GMS software that we'll be using, but this is conceptually how the calculations are done. Another one I want to talk about is the CHD package, the time variant specified head package. I don't have any drawings associated with this. This is a really simple package, and it's used to calculate a changing head boundary condition. So we've talked earlier about a constant head boundary condition when we were talking about the I-bound array. The original method for defining a specified head is for the cell where you have a constant head boundary, you give it an I-bound value of -1. And then for the head associated with that, it looks in the starting heads array. So through a combination of the I-bound array and the starting heads array, you can define these constant head boundary conditions. Now, the problem with that is the I-bound and starting heads array, those are not transient. They don't change with time. And so it only worked for constant or steady state heads. And so at some point later in time, they came out with the CHD package that allowed for specified head boundary conditions to vary. And it turns out you can even use this package to do steady state boundary conditions if you want. It doesn't have to vary with time. So there are two ways to do steady state fixed head boundaries, with the I-bound array or with the CHD package. Now, by the way, at this point I should pause and emphasize something here. How does a constant head boundary condition work? Well, it's either a source or a sink. Let's suppose I have a cell that I mark as a fixed head cell, and typically you would only do this to simulate either a river, a rather large river, or a lake. And the way it works is there's the water goes between the constant head boundary and the aquifer, and it's either going into the aquifer or out of the aquifer based on the head difference. And there's no barrier to flow. There are no sediments, or the sediments have about the same hydraulic conductivity as the aquifer itself. And so I'll try to remember to do this in one of our classroom exercises, but if you take if you take the general head boundary condition and you give it a really large conductance, which would, a very large value of hydraulic conductivity, you get basically the same results as you get with a specified head boundary condition. So the best way to think about a specified head boundary condition with either the I-bound array or with the CHD package is like a lake or a river with where the conductance is really large, and there's not much head loss between the river or the lake and the aquifer in question. And so we sometimes use these, especially on simple models we're doing in class, just to have a really simple approach to simulating these external water bodies. Okay, next we have the HFB package, the horizontal flow barrier package, which is used to simulate low permeability barriers such as faults, sheet pile walls, and slurry trenches. If you have a fault, over long periods of time, that movement of one side of the fault against the other creates a set of fine-grained materials at the location of the fault. And here's an example of a very visible fault. Those fine-grained materials can be a barrier to groundwater flow. There are cases where you can have a water table on one side of a fault be much higher than the water table on the downstream side of a fault. So as the water's progressing, for example, looking at our this photo up here, if the water is moving from left to right, you could have a large head drop from the left side to the right side because of the low permeability materials along this fault. And sometimes we have to simulate that. Another use of this is to simulate low permeability cutoff trenches, sometimes to encapsulate a site. Maybe we have contaminated groundwater and we want to make sure it doesn't migrate off our property. You can dig a trench and backfill it with low permeability slurry, and that becomes a barrier to flow as well. It doesn't completely stop the flow, but it it's a low permeability barrier that there's a certain amount of head loss as you go through that barrier. So how do you simulate this using the HFB package? Let's suppose we had a fault that looks like this, and we're looking down from the top of our model in plan view. What you do is you then identify the cell edges, not the cells, but the cell edges that most closely correspond to that fault trajectory. And you're going to get a piecewise linear representation as it goes along these edges. And then you mark each of these edges as a separate entry into the HFB package. And so, for example, suppose I have, you do this by identifying pairs of cells. So these two cells together would define this interface. These two cells would together define this interface, and so on. So if I look at my adjacent cells, and then the barrier is then applied to that cell boundary. And each instance is then defined by a pair of cells, is assigned what is called a hydraulic characteristic. If you think of that interface as having some thickness and area, the area is just defined by the cell dimensions, and the thickness is something that you would have to estimate. The hydraulic characteristic, H sub c, that you enter is the hydraulic conductivity of that barrier divided by the thickness. And then inside the model, as MODFLOW calculates flow from one cell to the next, it basically takes the hydraulic characteristic and multiplies it by the area, and then multiplies that by the head difference. And at this point, basically, we're looking at Darcy's law, as if you substitute back K over T for hydraulic characteristic, you have Ka over T, which is the hydraulic conductivity times the area flow divided by the length of flow times the head difference. And so that effectively is Darcy's law. And so those calculations are done internally. And so this is actually a pretty easy package to use. Setting up the input can be a little tedious. Again, a graphical user interface can automate this for you, but it's a really useful tool whenever you have a fault or other horizontal barrier. Okay, finally we have in terms of the packages we're going to talk about in this lecture, we have the EVT, or the Evapotranspiration package. And this is used to simulate groundwater loss from evaporation and transpiration. So this is only a sink, never a source. And the theory here is that if the water table is high enough, if it's near the ground surface, some of that groundwater can be lost through evaporation or through transpiration to plants, as shown here. If the water table drops, this behaves somewhat similarly to a drain. That loss only occurs if you have a high water table. If the water table drops, the evapotranspiration goes away, and it has no effect on your flow. And the evapotranspiration rate depends on how close that water table elevation is to the ground surface. And if it drops, then the evapotranspiration goes away. And if that water table doesn't come back, you could potentially lose your phreatophytes and have an impact on the ecology of the region where this is occurring. And so this is how the ET package works, EVT package. So we have, for each cell, you define an ET surface, which is typically the ground surface. You also identify a maximum ET rate, and you also identify an extinction depth. And the theory is, if the head in the cell is anywhere between the ET surface and this extinction depth, then there's some amount of evapotranspiration occurring. And again, this ET surface is typically the ground surface. And if you're at the ET surface, the evapotranspiration rate is at the maximum rate. And then as the head drops, it varies linearly all the way down to the extinction depth, and then it goes to 0. And so if the head is below the extinction depth, the evapotranspiration rate is 0. If the head is above or equal to the ET surface, it's equal to the maximum evapotranspiration rate. And anywhere between those two extremes, it just varies linearly. And so that is how the ET package works. We often call it the ET package, not the EVT package. And it's very easy to use and very useful. A lot of groundwater systems have some level of evapotranspiration occurring, and so this is a relatively common package. Okay, so that completes the set of packages that we were going to discuss in this lecture. So now you have a lot of tools available. All these different optional packages, you can simulate a pretty wide variety of conditions and sources and sinks in your MODFLOW models, and we're ready to build some models.